Right, we are recording. Okay, so hydrogen bonds. One thing that we must know about hydrogen bonds is that number one, it is the strongest. All right, it is the strongest. It's stronger than the van der Waals forces. It is the strongest bonds that exist within chemical compounds and chemical molecules. Okay, and which is very interesting when we start talking about melting points, as well as when we start talking about boiling points. Now, I must have you all know that this section is theory overload. All right, this is pure study work. If you do not study, if you do not make notes from your textbook, this section will not make sense because you don't know the theory behind it. Okay, so it's a lot of theory. Okay, so the reason why and what I want to begin with, the reason why hydrogen bonds are very, very strong is that when they combine with certain elements with high electron negativity, okay, if you look at the periodic table, the electron negativity can be found either depending on the type of um, periodic table you have. Sometimes they swap it up. Sometimes they put the electron negativity at the top. Sometimes they put it at the bottom, but usually the periodic table will have a key. For example, the one that's in the book I'm using from, if I look at the compound boron, which is the fifth element in the table, and it is in group 3, its electron negativity is 2. On my periodic table, it might be 1.9 something in your one, but it's my one has all round figures, mostly round figures. So it is 2.0, its electron negativity, and its atomic mass is at the bottom, which is about 10.8. So because I have a key on my periodic table, I can find the electron negativity there. So when hydrogen, H, combines with certain elements with high electron negativity, such as, if you look for example, when hydrogen combines with nitrogen, oxygen, and fluorine, all right? Right? If hydrogen combines, right, if we add hydrogen here, if we combine it, we all know the type of compounds that we get, right? We get NH3 if hydrogen combines with nitrogen. We get H2O if hydrogen combines with oxygen. And we also get hydrogen fluoride if hydrogen combines with fluorine. Okay? When this occurs, all right, it forms dipoles with greater polarity or stronger polarity. So greater, or we can use the word stronger polarity than, and I'm going to shorten van der Waals forces into VDW, than van der Waals forces. Okay, so that's the first thing that occurs. The second thing that we must note is we pay attention to the lone pairs. All right, the lone pairs of electrons that exists in, for example, nitrogen and oxygen. All right, we pay attention to the lone pairs. All right, so for example, nitrogen, okay, has one lone pair. One lone pair. And I'll draw it out here for you guys. If we remember Lewis diagrams, all right, if you should remember from grade 10. All right, we draw nitrogen. Nitrogen is in group 1, 2, 3, 4, 5. All right. Are that 5 bonds over there? Yes, it is. So it has 1, 2, 3. Obviously, valence electrons in the outer shell, and it has one lone pair. That is one lone pair. All right. And we look at oxygen. Oxygen being in group 6. All right. 1, 2, 3, 4, 5, and 6. We see that oxygen has two lone pairs. One over there, and one over there, pairs 2. Okay. So And fluorine has 3. So if I must draw fluorine, there'll just be 3 lone pairs. I don't know if everybody wants me to draw that, but fluorine is in group 7. It's part of the halogen groups. So just so everybody can see it, I'll draw it. Fluorine, 1, 2, 4, 5, 6, 7. It has 3 lone pairs. That one looks like a face. That one looks like a weird face over there. All right, cool. So nitrogen has 1 lone pair, oxygen has 2 lone pairs, and fluorine has 3 of these lone pairs. Now, what these lone pairs do, they are responsible for the repulsion between the bonds in the respective molecules. Okay, so we all understand forces of attraction and we all understand forces of repulsion. Am I correct in saying that? Talk to me, someone. Am I correct in saying that?
Yep.
Fantastic. Okay, so these lone pairs, and I'll put it up on here so everybody can write it down. Lone pairs, they are responsible. All right, for the repulsion between the bonds. Oopsie, not betweens. Between the bonds. All right. Now, when that happens of the respective molecules, thus making the H side or the hydrogen side of the molecule more positive. All right, and the other side more negative. So if the one side is more positive, the other side is more negative. That's kind of intuitive. Okay. As I mentioned, the dipole forces that exist between, for example, where are they? Over here, NH3, H2O, and HF are what is called, as we mentioned on top here, hydrogen bonds. Okay, and they are, like I said, they are the strongest ion dipole force. Sorry, they are the strongest intermolecular forces besides the ion dipole forces. That's hydrogen bonds. Very special dipole to dipole, by the way. I need to put this up here, on top here. That just because it's hydrogen bonds, that we still need to know what type it is. It's a special dipole to dipole force. I am the people's tutor, so do the people have any questions? I take silence is a no. So I can move on? Or do you still need to write some things down?
I'm good.
All right, thank you. Anyone else before I clear the board? All right, cool. Timothy, is there anything you'd like to add to that?
No, I'm cool.
All right, fantastic. And what I'll do is I'll just erase. Okay. Great. So, we want to talk about water. H2O. All right, water. We must draw water. I'm going to draw the Cooper structure. This is the correct way of doing it. Okay. It's bent or angular shape. And water molecules can line up with each molecule bonding with 4 others. All right. And for example, if you must have a look at, for example, if you must draw water in its Vesper theory shape, we'll have a big bubble. I'm going to draw it in 2D, of course, with a little dipole force there, positive. All right, this is a hydrogen. The oxygen would have obviously negative, and that'll obviously be another positive hydrogen dipole. All right. If I have another water molecule over here, all right, this will be obviously the hydrogen one. It will be the oxygen one to be negative. Looks like a 5, but it's actually that I'm trying to draw there. And that'll be, just fix that. That was horrible. All right, there we go. And S positive. All right, over here. All right, this figure shows hydrogen bonds between two water molecules. So these two water molecules had to combine. Obviously, we understand forces of attraction. We have a positive dipole there. We have a negative one here. So these two would attract between each other. This little dotted line here that I'm representing will obviously show what is called as a hydrogen bond. Why? Because this represents hydrogen. It's in the name, literally. All right? It'll be called a hydrogen bond. Okay. Another little fun fact is that in ice, each water molecule is bonded to 4 others in a tetrahedral structure. All right, with strong hydrogen bonds between the molecules. All right, now ice, we know ice can be melted with just a little bit of heat, but if you must take your fist and try and crush ice, it's not going to be very easy. All right, it's very, very strong. Ice is considered a solid, all right, because that's what it is. It's solid water. The only way you change that state is to heat it up. Then you change the phase of matter. Okay, so all you have to do is picture another 2 of these water molecules combined, and then basically that's what will give you ice, right? Because each water molecule is bonded to 4 others in what's looked like a tetrahedral shape, and that way, all of a sudden, like when water is freezing, picture it as like friends huddling each other. Okay, we got to stay together, we got to stick safe, and then they just find 4 others or 3 other friends. Each one finds 3 other friends, and then you have what is called ice. That's just a little fun fact. Hardly ever examinable, so don't worry too much about that. All right, exercise time. Any questions about water bonding to itself, or any questions about ice? Before we get into the exercise. Everybody seems good. Tim, are you also good? You don't want to add anything to that one?
I'm good.
Cool. Thanks, mate. All right. So what I'll do is for the exercise, how to make this exercise go a little bit, I wouldn't say a little bit long, but we want to try and make this exercise as interactive as possible. So I'll write down about 2 questions, do the answers, have a look at the answers, explain them, then put another 2 or 3 questions, and I've only selected 5 here for this one. So we can have a look at them quickly. Shouldn't take long per question. All right. So because we'll be done at 5. We got almost just over an hour left. So the first question in the exercise I would like everybody to do based on what I've just taught, a little bit of general knowledge, a little bit of grade 10 work, is why do we call the solid and liquid phases the condensed phases of matter? Okay, so we put that on the board. Why do we call the solid and liquid phases? Here we go, phases, that's an A, by the way. The condensed phases of matter. Can I fit that word in there? Yes, I can. Okay. And then question 2 is I'd like everybody to arrange the 3 phases. Obviously, we only have 3 phases, which we all know very, very well when we learned in grade 8 and grade 9 natural science. I want you to arrange the 3 phases of matter in order of increasing orderliness. Okay, that's a word we don't hear very often. Orderliness of particles, or of the particles rather. Don't panic too much. I will go through the answers if you don't know. Over here, put the answers down here at the bottom for each one. All right, so I'm going to give Timothy, help me on this one. How much time do you think we should give for these 2 questions?
About 5 minutes.
About 5 minutes.
5 to
Okay.
10.
Okay, cool. So at about 5:02, or about, okay, it's 1 minute now. So at about maybe 3:56, we can have a
cool.
look. We can have a look at the answers. All right. Let's go. Right. So let's get down to the answers. So let's have a look at number 1. So number 1, again, the question was, why do we call the solid and liquid phases the condensed phases of matter? So this is, you could kind of answer this question just based on the knowledge of what you understand about the word condensed. Okay? And the reality is that particles in the solid and liquid phase they are close together. All right, they are quite close together. Liquid not as close as solid. All right, but they are close together. And they have little space to move around. There you go, to move around. All right, so therefore based on that, if they have little space to move around, they cannot be compressed. They cannot be compressed, therefore they are condensed. All right, but we do know the other phase of matter can be, and that is gases. All right, so gases, they have what is known as larger spaces between them. If you didn't add this in your answer, it's still correct. If at least you got the first part right up until here, you can mention this in your answer as well. And this is also for learning purposes, is that gases have larger spaces between particles. And hence they can be easily compressed. Cool. Everybody understand the first question's answers? Anything that is unclear, please speak up now.
JP?
Talk to me.
The answer that I got is the attractive forces in liquids and solids leave little space between molecules, whereas in the gas phase, the molecules are closer. That is right there?
That is an acceptable answer. Yes, sir.
All right.
Thank you for that. Excellent. Okay, so if you guys get an answer, if you guys wrote down an answer, but it has the same context of the answer that I'm giving you, obviously I'm giving you memorandum answers, and it makes sense, You give yourself a mark. If not, you can check with me though. Perfectly fine. Question 2, I reckon most of you might have gotten to maybe a bit of trouble either in understanding the question or not, because it is quite a vague type question. But they asked us to arrange the three phases of matter in order of increasing orderliness of the particles. Okay, so in other words, from least orderly to most orderly. All right, so if we must rank them from least orderly to most orderly, we'd rank them like this. Gases would be at the least, then liquid, and then solid. Solid is the most orderly. If we must start with gases, we've mentioned it already in this answer. All right, they basically have maximum freedom of movement. They can move wherever they want to. Okay. If you just rank them, that answer is still correct. If you rank them in gases, liquid, and solid, that's also perfectly fine. But the reason why gases is the least orderly, they have freedom of movement, so there's basically no orderly arrangement. The particles all over the show. All right. Then we have liquid. All right. When particles can move past each other, but they are confined to the liquid. All right. If you must pour liquid into a container, all right, the liquid will take shape of the container. All right. So liquid, I'm writing small so I can fit it all in here. Liquid, they take the shape of the container if you must pour it in there. So it still shows that there's some order, but yet particles can still move past each other. And then we got solid, which is the most orderly. All right. Most orderly arrangement of particles. All right, and these we can find by the definite shapes that we get. If we must take, for example, shape of a rock. Rocks have shapes. All right, very solid. If you must even cut a rock in half, it'll come off in a shape. All right, rock, stones, gems. All right, take diamonds, for example, etc. Definite shapes. In other words, they cannot just be easily changed or manipulated. Questions about those two ones? Those were quite basic. Any questions, ladies and gentlemen?
I'm all good.
All right. Fantastic. Who got 2 out of 2? Who got the first one right and the second one wrong? Who got 1 wrong?
I got 2 out of 2.
Perfect. Perfect. Okay, like one person got 2 out of 2. Not sure about the others. I think the others are a bit shy. Maybe they want to talk to me in the chat instead. don't like hearing. Don't like their voices being heard. All right. Let's see what we got here. 2 from Jordan as well. Thanks, Jordan. I acknowledge. Cool. I'm going to go ahead and add another 3 more questions. Okay, we have another 3 more questions of this exercise before we move on to another. Lots of practice, even though it's online. Move that away. There we go. All right. Okay. Third question. is which forces are described as van der Waals forces, and give an example of each type. So which forces are described as van der Waals forces, and please give an example of each. I will be asking you guys 4 answers, especially on that one. See, that's the fourth one. Fourth one is, what is a hydrogen bond? And the fifth question for this exercise is quite a lengthy one. Okay, so please tell me, how does the presence of hydrogen there we go. How does the presence of hydrogen bonds in water influence the properties of water? A little bit of a brain teaser. All right. Timothy, help me on this one again. Okay, we've got 3 questions here, 3 bad boys. How much time do you think we should give them? It's 4:06 now.
Okay, 10 minutes?
10 minutes. All right, so at 16 minutes past, we'll have Q&A. Thanks, guys. Good luck.
Okay, go.
I'll pause recording again. All right. Got the dipole to induced dipole forces. And an example of that would be the hydrochloric acid that is bonded to a chlorine. All right. We obviously know chlorine can't exist on its own. It bonds to another one of its mates, Cl2. And the last one, which most of everybody knows it as instantaneous. All right, back in the day, I knew them as London forces. And an example of that one would be Cl2 to Cl2, so chlorine bonded to chlorine. All right, so that was the first one. So good job if you mentioned all 3, 100%. I was just looking for the last part, which was the example of each. Cool. The next, going through question 4. Question 4 was, what is a hydrogen bond? Obviously, this question is asking basically for a definition. So if we got a question like this in the exam, it will probably look like define hydrogen bond, okay, or give the definition for hydrogen bond. So all we need to do here is make sure that we state all the points that obviously define hydrogen bond in order for us to get maximum marks, of course. So the first thing that we need to explain here is a hydrogen bond is formed, okay, when hydrogen combines with certain elements with high electron negativities. Now there's 3 elements that have very high electron negativities, all right, respectively nitrogen, oxygen, and fluorine. Okay, now we all know what compounds or molecules that we get when hydrogen forms with nitrogen or oxygen or fluorine. We get NH3, which is ammonia, H2O, which is water, and hydrogen fluoride. Okay, so we get those compounds, which are also known as dipoles. Okay, now another thing that we also must mention when we are defining hydrogen bonds, they are stronger than our normal van der Waals forces. Okay, in other words, they require a lot of energy to break these molecules apart. Question 5 was, how does the presence of a hydrogen bond in water influence the properties of water? The first and probably one of the most easiest things to remember is that it influences the melting points and the boiling points. Okay, so water, we all know, has a very high melting point and has a very high boiling point, okay, because hydrogen is such a strong bond. Water boils at only 100 degrees Celsius. That's when water starts boiling, okay? 100 degrees Celsius is very hot, okay? Very, very hot. Another thing to note as well is that water does not evaporate easy, all right? Evaporation occurs, all right, especially water vapor occurs if you boil a kettle, right? You boil at 100 degrees Celsius, then water, you can see evaporation only starting. Maybe as the temperature is reaching 100 degrees Celsius, the water is starting to evaporate into water vapor. We also know that water does take a long time to evaporate if we watch the natural phenomena. We monitor droughts within our own within our own planet, right, own country, etc. How long it takes for water to eventually evaporate into the clouds and then eventually come back down as liquid water again. Also, water is a dipole, and with that being so, water can obviously dissolve other polar molecules, so we can get aqueous solutions. All right, so we can dissolve water with, for example, sugar can dissolve in water. Okay, salt can dissolve in water. Okay, we can mix other liquids with water as well, and they will mix with liquid together. But specifically talking about dissolving, okay, is salt and sugar dissolve in water. In other words, it still looks like water, but obviously a separate note from the physics or the chemistry, obviously it will taste differently, okay? But water definitely dissolves it, all right? Substances such as sugar and water. With that being said, that does conclude our little exercise on chemical change, sorry, not chemical change, intermolecular forces rather, and matter and materials. Thank you so much for joining me on this session, and I will see you all next time.